what we're doing today is a transient analysis setup in FloEFD. And some of the key items here that we're going to cover are how to activate the time dependency in FloEFD, how to set up the finish options for the simulation, obviously as a transient versus, let's say, a steady state, the saving options for the results in a transient. Okay, there's a reason why you're doing this. You need to see results, over time. The calculation control options, where these options are for the transient, they are very similar to, steady state options, but obviously there are some that are specific to the transient. The time step settings for the transient, and then results files, where they are located, how to use them, and then obviously for post-processing, how to load results files. Okay, everybody should be able to see this. We're in the presentation now in the PowerPoint. All right, so in the activation for the transient, there are two ways to activate the actual feature. The time dependency feature is obviously one of the features in our general settings, but it can be activated during the project wizard for a new FloEFD project. Just like you would start up a steady state, you can step through the project wizard, answer all the questions, and activate the transient time dependency there. But more often than not, when you're ready to run transient analysis, you've probably already run this model as a steady state. It just makes more sense, and it's just the right progression to take. So in that case, we would clone the model, clone the project, and then just activate the time dependency feature in the general settings of the existing project that's been cloned. This is definitely the most typical way of doing this. 99 out of 100 times, you're going to set up a model as a steady state. You're going to apply all the settings, heat sources, goals, post-processing. You're going to do all that work, make sure it runs, it has reasonable results, things are posed well, boundary conditions make sense, and then take that, clone it, make a new project, and all you need to do then in the clone project is update the settings for a transient. That way, all of the work has been done. Okay, and I'll show you the difference when we step through the sample model between going through the wizard and the clone project, and then where the controls are, because you still have to activate some controls. Okay, it's not all done for you, but it just makes more sense in that natural, method of going from one to the next in the clones. We're going to use the calculation control options for the adjustments of the transient. That includes the finish options. What are the criteria to stop the simulation? It's going to be different than a steady state, but obviously you're going to have your own criteria, whether it's a physical time or convergence or something like that. How do we save the results? How often do we save results? And what do we want in the results there? Basically, what files should we have? And then the time step settings for the transient analysis itself for the time step setup. So again, in our general settings and even in our wizard, we know that the physical features for the setup of the analysis are in that lower part of the window. Obviously, it includes heat conduction in solids, if we turn on radiation, and then obviously we turn on our time dependency. Okay, and we're going to do this two different ways, once through the wizard and once as a clone. The finish options, this is all part of our calculation controls. Okay, this is a typical settings in EFD. The finish options are defined automatically during the project wizard, but can be modified at any time. So when you set up a steady state analysis, even if you don't look at even if you're not sure what the finish options are for a steady state, they're always the same. And we usually adjust those for a transient because you want those to be a little different. And I'll show you the difference there. But again, they will have different settings here for a steady state versus a transient, and that depends on what your criteria are going to be. And whether you're running steady state or transient, it's always a good idea to check the finish options before starting the actual simulation. Take a glance at this again, open the window, make sure it's set the way you intend it to be. Sometimes I run analyses as a test with just 10 iterations or 5 iterations, so make sure it's not set that way. I want to go back and check it, that I'm not running just a small test or a short run. I have to go back and check it. So it's always a good idea to open this window up and double check what you're running for what simulation, what the finish options are, and if it makes sense for your current analysis. One of the nice features that you can use in the calculation controls under the finish options, especially for a transient, this is a really nice feature, and I can show you how to do this later, is the ability to use a goal satisfaction as a finish option. And what that means is instead of instead of running a transient for a desired physical amount of time, let's say 1 minute or 10 minutes or an hour, you can actually run a transient until, or make it stop when a specific goal reaches a value. So for instance, we may have 10 or 20 goals in our model, but one of the goals, or the most important goal, is the max temperature of a chip. So if that's the only goal I want activated, and I can turn that to a manual adjustment here, that means I can control the finish options to tell EFD to stop the simulation when that max temperature of that chip reaches 88.0001 degrees. Once it crosses 88 degrees, stop the analysis. So that tells me, when the analysis is all said and done, that shows me how much time it took to reach 88 degrees. We don't know. That's an unknown, okay? So I can't run it for a specified physical time because I don't know how much time it takes to reach 88 degrees or 350 or whatever it may be. So this is a good way to let EFD stop for you when it does reach that temperature, that desired temperature. I don't need to go over that. I just need to know how much time does it take to get to that 88 degrees. Again, it's a really nice feature. It's used a lot in transients, so you don't have to put a specific time frame in here, okay? Another feature that's available with the transient analysis is the fan control. So when you're running a time-dependent analysis, the fan option now has a toggle which allows it to be turned on or off according to a goal, for instance. Okay, again, another feature where you can control the fan during the transient. You have a goal dependency which is applied with a control value and a deadband. So again, I may have a fan that I want turned on from the beginning, but once the max temperature of the chip, again, reaches a specific value, I want the fan to go off or on, okay, one or the other, obviously. So you put your control value here with the plus or minus a deadband, so within 2 degrees of 88, and when the max temperature of the chip reaches 88, turn the fan on, or turn it off, or when it's below 88, turn it off again, and so on, okay? So you can control a fan option in EFD with a toggle. And again, an application, a typical way of using that is a fan activation due to a temperature rise, okay? Again, really, really useful feature, and it's only for a transient. Same thing with the heat source. When a transient analysis is being run, you can toggle the heat source to be on or off according to a goal, okay, a function of goal. It's dependent on something you've prepared. Again, there's a control value and a deadband. So again, this is typical application would be a thermal shutdown in electronics. So when your surface goal for heat transfer rate reaches 10 watts plus or minus 1 watt within a range, turn on or turn off that heat source. Okay, again, really nice feature, very easy to apply, and it's all part of a dependency in the heat source item definition. I'll show you the window when we get to that. And it's real easy to open and put those. As long as you have the goal, that's the most important thing, is you have to have those goals predefined. They have to be there so you can select it and say, okay, when that goal reaches this value, turn the heat source on or off. The results files, again, these are going to be controlled, or how often they're written is going to be controlled in the calculation control options. So typically when we run a steady state analysis, we're concerned with the end result. We have one results file, and that's the end result. That's all the data we need for that steady state. For a transient analysis, you're not always just interested in the end result. You're usually interested in the progression of temperature and velocity over time. You want results at interim locations. But by default, EFD is only going to save the final results file. So in our calculation controls, we have to basically determine the method of saving results, the interim results files. Okay, how are we going to save these files? According to time or iteration. The frequency of saving the files, how often do we want to save? Now, in any transient simulation, the more files you save, the more information you have, obviously, over time. And the smoother you'll have, the smoother results you'll get when you create your animations or you're looking at different time moments. But again, you have to be careful with that. You want to be conservative, because every time you save a file, whether it's every half second or tenth of a second or whatever it may be, every time you save a file, EFD is actually saving a full results file, just as though it was the end result, okay? And those results files are the largest files in the subfolder, in your instance project folder. So you don't want to go crazy and save 10,000 of these files, because it will fill up the disk space. And, these files may be 20 megabytes, 50 megabytes. If the model is really detailed, you know, it has a lot of cells, it has a lot of features, physical features involved, the results files could easily be upwards of 700, 800, 900 megabytes easily, okay? Which means that as you save each one of these in the frequency, it's going to just save another 900 megabyte file, another 9, and so on. So you want to be careful with that. You'd like to have, you know, as many as you can for the overall result, but you don't want to have too many. The interim results can be saved at any time moment and loaded for post-processing. So in our EFD post-processing, instead of just, you know, loading the final results file, you can use the load time moment feature in EFD and select the desired time moment. So if you have a results file at every second for a 10-second run, you can load any one of those timestamps at any one time. You can only load one file at a time as far as the results. So you can view cut plots and surface plots and, you know, flow trajectories for any one time moment at a time in your graphics screen. Okay. Check the results folder for the saved file. So I'll show you where that, you know, where the files look like. Obviously, they're going to be in your instance folder, the subfolder for results. Those files can be deleted if they're not needed. So after you've done your post-processing, if you don't need those interim results files, you know, the list of files, you can delete them at any time. You can actually, you know, archive the files for future use or backup, and then obviously when you do that, you could always delete them afterwards as well. Okay, so they're not always needed. You can, you know, use them for your post-processing. When you're done, you can just delete those files at any time. The time step settings, also in the calculation control options, the time step is actually defined one of two ways, either auto, which is on by default by EFD, or manual, okay? So when EFD defines a time step, typically it's a very small time step to start on the order of, you know, 1e to the minus 5 or 6 or maybe even 7, depending on the model, physics, and features. But usually, you know, we recommend using some sort of manual adjustment to that time step. That way, number one, you know, you give it a better turnaround time. So if EFD were to run your analysis with a default time step for the entire duration of the simulation, it could take a day or two, maybe days, because it starts very small and it increases very slowly. So the idea is, even though we want it to start small anyway, because that's the best way to get the most accurate answers at the beginning of the analysis, you do want some manual intervention here to increase the time step, you know, ramp it up slightly, a little faster than what EFD would do, okay? So there are 3 manual options included in the time step settings. The first one is using a constant value. So you can prescribe a constant time step value for the entire duration. Again, typically you want to start with something very small, unless it's a conduction-only model where you can use a larger time step. You're allowed to do that. Maybe, you know, 1/10 of a second, you know, 0.01 seconds, and that's a little larger. But when you're running something with, you know, flow and thermal involved, you usually want to start, like I said, with a very small time step and ramp it up slowly. An idea of what's a good time step to use, there's a formula that you can use where you would take the smallest cell size in the model divided by the max expected velocity of the analysis. So if your smallest cell size is, let's say, 0.00625 inches, and that comes from knowing our base mesh cell size is 0.2 inches, and we're using 5 levels of refinement, that divides itself into 0.00625. So that's my smallest cell size. And let's say my max velocity, maybe I have a fan and I know what the expected velocity of that fan should be, or I've run one iteration and I know what I'm getting out of the fan is 24 inches per second. So taking those two numbers, our reasonable time step size should be 2.5 e to the minus 7 seconds. And that's a typical starting, especially at the start, okay? So again, you wouldn't want to run the entire duration with that time step, but it's a good way to start, and then you can ramp it up slowly over time. So that's using a constant value. The second method of a manual option is a table dependency, and that's using defining the time step as a function of time or iteration. And this is more of the suggested way to do this in the manual options. So the idea here is to include a table as a function of either time or iteration. I use both, but time is usually more direct because I know how much time I'm going to need. And at different time points from 0, let's say, to 60 seconds is my total physical time, I can prescribe a time step that starts relatively small, 1 e to the -5, and then ramps up, you know, a little quicker than what EFD would do, and then even, you know, the next ramp up from 1 to 60 is at a different rate. Okay, and I have a linear interpolation between the 2 points. Again, this is just recommended, and it just makes more sense because it's going to give you a quicker turnaround time without having to wait days or, you know, 12 hours, maybe just 2 hours for an analysis. Okay, this is a typical way to do this. And the third way would be a formula dependency, where you can define the time step according to a formula. Let's say based on iteration number times, you know, 0.001, or some other formula. So that you can explicitly enter a formula here, and that will be your definition of your time step. In the results for post-processing, we have our loading time moment feature. So the results can be loaded for any saved time moment. As long as you have those files saved, EFD will know where to look for them and which ones are available. So you're going to just right-click on your results item in your EFD tree and click on Load Time Moment, and that will give you a pull-down menu where, as long as those files are saved and they exist in the results folder, these are the files that will be available for you to load the results from. Okay, so there would be 10 files here, and each one is, you know, is the same size file, and that each one contains all of the data at that timestamp. Okay, real simple to do, and you can only load one timestamp at a time. So only one results file at a time. Unless, you know, you're doing animations, that's a different story. EFD does that for you, but that's loading them at different instances and creating an animation. Results goals. So goal plots can also be viewed by physical time instead of the default setting of iteration. So typically when we're post-processing and we plot our goals plots, typically that abscissa item is set to iterations by default. But as a transient, we can change that to physical time, and that way when we plot our goal plot, you know, this one is just for the max temperature of the main chip, we can see the progression of temperature over time for 10 seconds from the starting, you know, 50 degrees start initial condition, and in 10 seconds it reached, you know, 60.5 degrees. Okay, so it increased about 10 degrees over 10 seconds. Okay, so we have a physical time, very easy to do. That way all of your results are loaded with respect to physical time instead of iteration, because for a transient, obviously, it makes a little bit more sense. Okay, so we'll step into the example model here. If you have any questions later, today, tomorrow, next week, you can always email me directly. You can also submit a service request on Support Center, and someone will obviously reply to it. You know, one of the user support engineers in the group, or you can call me directly. Either way, and we'll probably open a service request anyway. But you can do it yourself right through the Support Center. There's also some other resources and downloads there that you can access, and they might answer your questions as well. So let's get into our sample model and do the setup here. So this is our typical FloEFD tutorial for A2, the conjugate heat transfer model. Everyone has it in their installation folder for the examples. I'd like to use it for the transient because it's just a very simple model to use, and I can apply different features. It's not a transient example, but you can practice on this as well. It's very simple. So I've run this model as a steady state. It's already set up. I know all of my conditions are here, my materials, my boundary conditions, my heat sources, and my goals. I have everything I need. It's run as a steady state, and it works. The results are reasonable. The meshing is reasonable. It does what I expect it to do. Okay? Now, I can take this one step further and go to the transient. But before we do that, let's say instead of doing that, I go through my wizard. This is the typical way we start a project, is using the project wizard. So I'm going to show you the differences between the two. So if I start a project wizard now, start my new project, project 1, set up my units, and then get to my physical features, turn on my heat conduction, and then turn on my time dependency. Okay, once I turn that time dependency on, it shows me 2 more features here. Okay, the first one is the total analysis time. What is the total physical time that I expect this simulation to run, to represent? 10 seconds physical time. Okay, whether it's 10 seconds, 60 seconds, an hour, whatever. Right now it's in seconds. You would put that in seconds here. That's my total physical time of my simulation results that I expect to see. The second feature here, the parameter is output time step. This is the results file. How often do I want a file to be written during that 10 seconds? Every half second, every 1 second? And knowing that I'm running this for a 10-second total time, by defining an output time step here, I know how many files I expect to get. I should get 20 files here, okay? And that's not, going crazy. I'm not putting a 1/10 of a second and get 100 files, or I don't need that. So at a half second, I should have 20 files, okay? Again, if I put a smaller value there, I'll get more files, and that will give me a smoother progression over time of temperatures and velocities. But for a test model, I can keep it, pretty coarse here. So every half second, save a file over the total 10 seconds, and say next. Obviously, add our project fluid, our default solid, whatever it may be for now. Okay, and say finish. Okay, so we've gone through our wizard, and it set up our new project, project 1, in our instance tree here, the configuration tree for EFD, and then we have our input data tree at the bottom. And obviously, even though I've set it up for the transient part of it, I really don't have anything else set up as far as conditions yet. I have to step through this and apply all of my materials, heat sources, goals, and so on. So there's still a little bit of work to do here, okay? So it's not like I'm done and I can just go ahead and hit the run button. I still have to set the model up. That's why, let's go back and activate our steady state. This is why it makes more sense to do this as a steady state, make everything, set up all your conditions, even do your post-processing. Then let's clone this. Let's right-click on that steady state project, hit the clone button, call this one Transient 1, for instance, say OK. And now I have a new instance as my transient model, that's going to be my transient model, with all of the duplicated and cloned items from my steady state. I don't have to add any conditions. Everything is here. I just need to adjust this model or simulation so it's ready for a transient run. I'll just save it real quick, okay? Much easier, much more direct, and it just makes more sense. All right? So I have my clone project. Everything is here. Let's go through and set it up for a transient analysis. So we don't have to step through the wizard. That's been done already. We need to go to our general settings and start adjusting the parameters. So we open up our general settings. Here's our first window for the general settings of analysis type and physical features. And here's my time dependency. I just need to turn that on. Okay. Now, when I turn this on, we don't see those two parameters show up. So that basically means you should know already where to adjust those. Those are other settings now. They're not in the general settings. Those are somewhere else. And EFD is expecting you to know about that. So if I just turn this on and say OK, I can run this, but I haven't really set up the transient yet. I haven't done anything other than apply transient, but not set up the time step, not set up the total time, not set up my results. So you have to keep that in mind. Once you do this once or twice, it'll be, just a habit. But EFD expects you to know that. You've applied your transient feature. Now go ahead and set it up completely. Okay. So where are those other parameters that we need to adjust? Well, those are all under our calculation control options. And whether you get them from the command manager or under flow analysis, calculation control options, it's probably in a couple of different spots under each system under different menus. Okay. So our calculation control options have a few tabs here, but the first one is the finish tab, one of the more important ones here. And the finish tab basically controls how the simulation is going to stop. Now, what's here right now are the default settings for a steady state. A steady state is going to stop when one of two things happens. One of these things has to be satisfied. Either the goals are converged or EFD reaches a max of 4 travels in the simulation. That's a steady state setup. I'm going to do this as a transient, so I'm going to turn those off. I don't want to be controlled that way. I want it to be controlled by physical time. This is my total physical time of my transient, 10 seconds. Okay, that's the parameter I need to tell EFD to run to simulate this analysis for a total physical time of 10 seconds. And that's all. I don't need to do anything else. I mean, later on I can show you we can combine these, but right now I want this to run for 10 seconds. I still have goals that are active here, but they're not convergence goals. They're basically just monitor goals now. Okay, so I can still use those, but they don't apply in our convergence and our stopping criteria. Okay, so that's the physical time, total 10 seconds. Now we have to set up our results saving. Where do we save our results files? Well, that's also in control options here, but it's under the savings tab. So the fourth tab is a savings tab. At the top of the window here is the backup files. I usually don't change this and I don't rely on this. This is just the automatic backup for the program. And it says to save a backup every 100 iterations. Again, I don't rely on this. This is not what we're looking for. That's on all the time. That's just like a fail-safe, something crashes, but again, this is not what I would rely on. The middle section is the one we want right now, the full results. Okay, this is where we're going to tell EFD to save interim results files during our transient, okay, during the simulation. And we can do it one of two ways, either by a periodic method or tabular method. I typically go by periodic again, but I can do both, and I'll show you what that means. But I usually start with periodic. It's just the most direct and it makes most sense. And once we activate periodic, we can also we can change it by either by iterations, physical time, or wall clock. Typically, I go to physical time, and then I can start telling EFD how often do I want you to save interim files. Starting at 0 seconds, save a file every half second. And just like I did before in the wizard, if I know I'm saving every half second and I'm running for 10 seconds physical time, I should get 20 files. This I can predict how many files I'm going to get here. Okay, that's why I like using physical time and obviously a frequency that I can predict. If I use iteration, we don't know how many iterations this is going to run. It may take 1,000, it may take 5,000. We don't know to get to that 10 seconds, depending on our time step. So if I choose iteration, I really can't predict how long it's going to take or how many iterations it's going to take to run or how many files it's going to create. I don't know. This way I can predict how many files I should have. Okay? Now, if you wanted to use tabular, we can use either or even combine it. So let's say, even though I'm doing this as a periodic frequency, okay, every half second, I can also save a tabular file. So for instance, even though I'm saving every half second, maybe I'd like to see a file exactly at 7.3 seconds. Oops, what did I put there? 7 hetero. Oh, I'm sorry, because I had iterations. I'm sorry. So this make that physical time, and now in my table, there you go. I wanted to put 7.3, just to make it something odd. Okay, so it's an odd number, 7.3. Okay, so not only is it going to save every half second, but when it gets to 7.3 seconds or passes that first time, as soon as it passes 7.3 seconds in physical time, it's going to save another file for me. So I'm combining these two. I'm using them together. You don't have to do that, but it's available. All right, so again, it's just another way of doing it. You can prescribe it or just give it a frequency. Okay, so that's the most direct way to do it. So we have our saving, we have our finish option, and now we go to our solving tab, the third tab. And this is the tab where we're going to define our time step. Again, the time step is defined as automatic by EFD, which means it's going to start very small and gradually increase very slowly. And that's okay to start. And we can change these settings at any time during the analysis dynamically and let it update itself. But the more typical way of doing this is using the manual option. And then with the manual option, we have a few ways of defining our time step, either as a constant through the entire simulation or as a function of time, iteration, or formula definition. Again, I typically go with function of time because it's something that I can easily prescribe. So at time 0, start with a time step of 0.001. At 1 second, increase it to 0.01. And then by the time it gets to 10 seconds, let's do a 0.1. And I can show the chart here to show my ramp up. Okay, so I'm forcing the time step to increase quicker, obviously within less time frame, and start a little larger. But again, for this test model, it's okay. I would probably still start, e to the -5 or 6. That just makes more sense. It's better for the calculation, and you get more accurate calculation in general. But for this case here, just to show for the test, I would do something like this. Okay, so this is recommended because, you know, something that you can get results in maybe 2 hours or 3 hours is better than waiting 12 or 24 hours. If you need it to run over a weekend, then that's better. Then obviously you have the time, the CPU, let it run. But if you need to, you know, do some design variations here, you want to get a little bit of quicker turnaround, this is what you would do. And I'm just going to bump this up just one more, so that way we're not waiting too long for this. Okay, so we have now even with the defined time steps here and the time start, EFD gives me a number of iterations that it should go to complete that time frame. So 2791, so it should run about 116 iterations here, just to get to that 10 seconds. Again, it's really coarse. I'm doing it really quickly, but that's going to run, you know, for our test case. Okay, so I've set up a manual dependency. My finish options make sense. Let's say okay. Save what I have here so I don't lose anything, and let's hit the run button and run this. Should be pretty quick. Okay, we have our info window, our log window, our goal window that I usually bring up for the goals, and our preview plot. A couple of things that you'll notice here that are not in the steady state analysis are these two parameters right here. We now have a physical time stamp that shows us what the current physical time is that the simulation is at, and then the current time step being used. And you can see that increases gradually until it gets to the 0.1 because now it levels off at the 1 second. My current time is at 2.345, 6, okay? I even get a little warning here at the bottom saying that the specified time step is greater than what should be used. And that's just a warning. I know it's larger than I should be using a smaller time step, but for sake of a test, that's okay. We're just running this quickly to get some quick turnaround, okay? Iteration-wise, I'm really not concerned about how many iterations it has to run because that's independent of the time. Okay, I'm more concerned with the total time. We're at 6.8 seconds now. We have our cell makeup here, which is typical, just like in a steady state. Let me squeeze this in a little bit so we get a little bit more response of what's going on here for our max temperature of the main chip and the small chips over time. You can also change the abscissa here in the x-axis to be physical time in your goal plot. So not only in your goals when we do this in post-processing, but even here, our goal plot here shows 1 to 10 seconds, and it finished. It reached 10 seconds. Our physical time is 10 seconds. The solver's finished. We have our message, okay? That means we can go back into our model, and our results should be loaded. We know the results are loaded because the results tree is active, and it gives us a little note here that says the 4.fld file is loaded, and the timestamp is 10 seconds. So I know that the current file is my end result file. It's at 10 seconds, and anything I do now, any plots that I create now, are representative of that 10-second timestamp, that time moment. There's a little timestamp in the graphic screen here, which is shown by going to display and time info. That's what shows up, makes that show up, that little timestamp. So again, any plots that I create right now are representative of 10 seconds. This is temperature at the 10-second mark. Let me hide my model. Okay, so that's the temperature at 10 seconds. Surface plot showing temperature solid of some components, the boards, the capacitors, and so on. All right, so your post-processing doesn't change that much from a steady state. I can use the same plots that we had before, but now they're just showing results at different time moments. By default, it's going to load the 10-second, the final one. If I want to load a different timestamp or results from an interim file, that's where I'm going to right-click on results, say load time moment, and now I have a pull-down menu, and I should see 20 files available here, 20 different timestamps from 0 to 10 every half second. So if I want to see results at 6.5 seconds, highlight that and say OK. Now these results are representative of 6.5 seconds. All right. Again, you can only load one results file at a time dynamically while you're in real time here. When you're doing an animation later on, that's a different story. You know, EFD will string them together and make that animation for you. In the results, in the solver window, there is a way to have EFD save each one of these preview images for you. I don't have the properties now, but you can go to properties here and have it save these, and then you could string those along as an animation later on as well. That's something you would have to do separately as a third-party program. But you can string these along or have it save a bitmap or JPEG for each iteration, or you can adjust the frequency, and then you could string those along later on or put them into a program and make an AVI. Otherwise, you can make the AVI right in EFD with your results that you created, okay, those interim results files. All right, so nothing really changes as far as our results. We have our cut plots, we have our surface plots, we also have our goal plots. Go to my goal plot here. These are all the goals that we've used. Again, they're not used for convergence. They're basically more of a monitor here. But by default, EFD is going to plot these according to iteration, but I want to plot those with physical time. So now when I say show, I have my goal plot table, my summary table here of all my goals and the values. And if I go to history, I now have an XY plot, a graph plot for each one of my goals. And this was the, right here. So this was the goal plot for my main chip max temperature volume goal over 10 seconds physical time. This is the one that I right-clicked and I said save as image or copy, and then I pasted it into my presentation. All right, that's each one of these is now plotted according to physical time. These are the small chips max temperature, 50. They all start at 50. That was my initial temperature, and then they reach 60, 64 degrees. This one's about 65 or 60.5 degrees. All right, those are our goal plots. Another nice feature you can use here for the goal plot is if I right-click on goal plot and just say show, it gives me this little widget in the plot window that I can use for presentations or reports. So we have a little widget for my current goal or a goal plot one at a time. And if I click on the goal plot title, I can change it to max temperature of the main chip. And now I have a goal plot showing me showing me the max temperature of the main chip. And I can move the widget anywhere in the plot screen. So this is nice for presentations, reports, just like I showed before in the presentation in the PowerPoint. So that's your widget for goal plot. You just have to right-click and say show or hide, and that'll pop up in the window there. Again, anything that we do here in our post-processing is just like a steady state, but we're just looking at transient results, obviously, at a certain time point. If we go back to our heat source item, let's go back here to the main chip. All right, so there's the main chip. It was set to 5 watts. If we edit that definition, this is where we have our toggle. Okay, and the same thing happens for a fan item. If you have a fan item, you can toggle it on or off. It's always on by default. Okay, so in a transient or even a steady state, it's always on. But in a transient, you can set the dependency so that it turns on or off according to a goal. So for instance, when my max temperature of the main chip reaches, let's put 88 degrees in here, turn off the heat source. Okay, so I can control that heat source, that main chip, when it reaches 88 degrees, at that plus or minus 1.8 or 2 degrees Fahrenheit. Okay, that's how you control a heat source or a fan according to a goal. That's the heat source. The fan is the same thing. We have a fan item here. It's a fan, internal fan definition. And here's the toggle, always on, and same thing. If I click on dependency, I can control that according to a goal. I can even control it according to time. At time 0, the fan is on. At 5 seconds, turn the fan off, and so on. And that could be periodic as well, which means that every 5 seconds, it's going to turn off. I should put 4.99 and then turn it off, and then turn it back on at 10 seconds. Okay? So you can control the fan by as a function of a goal or as a function of time. On, off, on, off. And the same thing with the heat source. You can do the same thing here too. Okay? So those toggles are there because we're in a transient. You don't see this in a steady state. It's not there. It's just always on in a steady state. Okay? So we have our items, our goal items, our results, our plots, everything that you would do here just the same as you would do in a steady state. Let me say that. if you do open up the animation tool for, let's say, for the animation of the surface plot here, let me go back. I think I made one here in this one. Let's load the results here. I think I have the same plot for surfaces. Say show all. Okay, and I created an animation here. So when we look at our results files, we know that we have interim results here. Where are those files and what do they look like? So if I go to my project name and I right-click and say Open Project Directory, this is the results folder for this project. Okay. If I step up one folder level, this is my parent folder of my parts and assemblies, and just like anything else, we have our subfolders. These are the EFD results subfolders, one for each instance or project. EFD knows which one belongs to which folder, so you don't have to, search for it. This one that I'm in right now happens to be Project 2, so when I go to that Project 2, I have most of the files start with a 2 because it's obviously relative to the folder, and then the extension. The main results file in any steady state or transient, the main results file is the FLD file. That's the end result, the 2.FLD. And in this case, it's about 7 megabytes. If I look lower down inside the folder, I should see these files called R_000 with the number. These are the interim results files. The number is the iteration that it was written, okay? And there should be 20, or 19 plus the final one, there should be 20 of these files. And there are 19 selected now, okay? And each one of these files is about the same size, 7 megabytes, because they are all, complete results files. They contain everything in the results, just like the end results file, all right? So these are the ones, you don't want to go crazy and have 1,000 of these, but obviously the more you have, the smoother your progression will be, or your distribution of temperature and velocities over time, the smoother that will be, okay? So, there's a little, you have to kind of compromise. Now, when I strung together, I put together an animation for my surface plot here, it looks something like this. This is an animation over time from 0 to 10 seconds of the surface plot showing temperature solid, okay? This is done in the animation tool. That's done where EFD will string together the results files according to time frame and then put them into an AVI file for you, all right? And again, that's typically done in the animation tool. You're going to open up the animation tool, step through the wizard. It's going to create your control points for your results file, okay? And then you're going to insert control points for the surface plots. This is a timeline. It's like a video editor. The red screen here is how you control what's being recorded. Whatever falls within the red screen, that's what you're going to record, okay? For instance, if I wanted to, let's X out of this, I could even, let's put that gold plot back in there. I mean, that could be part of our max temperature, okay? So let's do something like this. And then let's go back to our animation. Let's see if that opens up the same way. Okay, and then you have your animation title here for the file that you're going to create. Animation 3, 4, make it more specific to the name. And when you hit record, oh, that gold plot didn't stay there. I thought it would stay there, but it doesn't. Oh, you know why? Because I have to actually activate it. Let's see if I activate it here. Is it? Oh, it is. Let's see. Let's insert control point. Let's see what happens here. There it is. Okay, and then we'll hit record again. It's going to ask me if I want to override it. Yes. Oh, there it is. And you can see the vertical dash line moves with the time. Again, it's a little choppy, it's coarse because it's a very simple model and my time steps are relatively large, but that's how you would create an animation in a transient versus a steady state. It's a little different, okay? All right, so we're at 45 minutes. I think I covered everything in the presentation.